Hello class. Today we're going to be discussing section 1.1, which is real numbers and operations. Our objectives for today is to use a number line to graph and order real numbers, and then also we will identify properties of and use operations with real numbers. But before we begin, I want to relay to you that you need to know you can rewind this video if you missed something. If you didn't understand something, you can go back and rewind, and you can also take notes. Even though you'll have the PowerPoint, you should also take notes so that you can refer back to make sure that you didn't miss anything in the PowerPoint. The first thing we are going to talk about is that what are real numbers? Real numbers are numbers most often used in algebra. There isn't anything as a fake number. The other set of numbers that we're going to learn later are called complex numbers. Real numbers can be graphed on a number line, and you graph them on a number line using a point. The number line is usually labeled with 0 in the middle, and 0 is called the origin. The numbers on the left are the negative numbers of 0, and the numbers on the right are the positive numbers of 0, as you can see on the number line that just came up. So 0 is your origin, the negative numbers are on the left of 0, and the positive numbers are on the right of 0. 0 is in the middle because it's neither positive nor negative. So 0 separates the negative numbers from the positive numbers. There are subsets of real numbers. And so all numbers are real, but there are subsets of real numbers. For example, whole numbers are a subset of real numbers. Whole numbers begin with 0 and move to the right or move towards the positive numbers. And this ... means that this continues on forever. One way that I like to tell my students to remember whole numbers is that there's a letter O in the word whole, and then whole numbers begin with 0, which looks like the letter O. So that's one way that's helpful. And hopefully you can come up with your own ways that will be helpful to help you remember what a whole number is. Integers is another set of real numbers. And if you notice, whole numbers are in integers. The only difference is that integers also includes the negative whole numbers. So we have the negative side of 0, we have 0, which is neither positive or negative, and then we have the positive side of 0. And so those are your integers. And again, this ... means that it goes on forever, and this ... at the end, at both ends, means that it goes on forever. One on the positive side, one on the negative side. And then in the slide before that I forgot to mention, we saw, let me go back, we saw this symbol here. This symbol means that, again, here's the 3 dots, and the negative side will go on forever, and it will go on towards negative infinity. This is an infinity symbol. It looks like a sideways 8. We use an infinity symbol because we don't know where numbers end. Same thing on the positive side. So this is, it looks like a plus sign, but we consider this as positive infinity. And again, we use infinity because we don't know where numbers end. And so positive and negative infinity will represent the largest numbers that we could think of on both sides of the number line. Another set of real numbers is called rational numbers. As you can see, rational numbers can be fractions of 3/4. It can be a fraction of 1/3. It can also be a fraction of -4/1, which is just -4. So hopefully you can see rational numbers can be fractions, and it can be integers. Also, if you notice, if I turn 3/4 into a decimal, which is 0.75, it terminates. So rational numbers stop. Or rational numbers, as you can see, 1/3 is 0.3 repeating. That's what the ... means. So rational numbers do two things. It either terminates, so you can have a fraction of 3/4, which is 0.75 when you turn it into a decimal, or it can repeat, but it has to repeat with the same numbers. And I like to tell my students that rational numbers are rational. They make sense. 0.75 is something that we can concretely get to. 1/3, even though it goes on forever, but it repeats with the same number, so it has some concreteness to it also. This fraction of -4/1 is just -4. -4 stops, so it's also a rational number. The next set of real numbers is called irrational numbers. And irrational numbers, there are real numbers, but they are not rational, such as radical 2 or the square root of 2. The square root of 2 is 1.414213,562. And if you notice, I just ran out of space on my calculator, but if you put this in your calculator, you'll get the same thing I got. I just ran out of space on the calculator, but this number does continue. But if you notice, none of the numbers repeat after each other. So since none of the numbers repeat after each other, then it is irrational. It doesn't make sense, meaning that it doesn't stop like a rational number, and it doesn't repeat. Same thing with pi. Pi goes on forever, but the calculator could only go up to this last digit of 4. So when you write rational numbers as a decimal and irrational numbers as a decimal, you're looking for certain things. You're looking to see if it stops like 0.75 or if it repeats like 0.33333. They're rational. But if it doesn't stop and doesn't repeat, then it's irrational. So here are some examples, and hopefully you can get through these examples. You can pause at this time and try the examples, or you can keep going. But A, hopefully you can see that A is a rational number. If you continue, B, which is radical 2, which we just talked about, is an irrational number. C, which is 2.7, and again 2.7 stops, and so that's also a rational number. And D, we have -4/1, which is just -4, and that should be an integer. It should also be a rational number, which I just neglected to write, but hopefully someone caught me that this is also a rational number because it can be written as a fraction and it's also an integer. And then E, 0, and hopefully you saw that 0 is a whole number and an integer. Next, we're going to graph real numbers, and in order to graph real numbers, you should turn all the numbers into decimals. -4/3 is a fraction, radical 2 is a radical, and 2.7 is a decimal already, so that works in our favor. So here's our number line, and again, hopefully you remember that 0 is our origin. Our negative numbers are on the left and our positive numbers are on the right. We turn -4/3 into a fraction of -1.3, and as you can see, the 3 repeats, and -1.3 with the 3 repeating is in between -2 and -1, and so we plot our point in between -2 and -1. And notice I didn't write -1.33333. I wrote the original number. Also, radical 2, and like we said, it's also called the square root of 2. It doesn't stop, but we are going to have to approximate so that we can get a nice decimal that we can work with. And we will approximate it to 1.4. and that is in between 1 and 4. I'm sorry, that's in between 1 and 2. And again, I didn't write 1.4, I wrote radical 2. And I put my point on the number line, and that's important. A lot of students want to put their point above the number line or below the number line, but you should put your point on the number line. And finally, the plot 2.7 is in between 2 and 3. And here we have 2.7. And then if you have any questions, you can refer to your book on page 7 so that you can get some practice on problems 4 through 7. Next, we will go into properties of addition, where A and B and C are numbers. So we have the closure property, where it's the closure property of addition. So A plus B is a real number. And all that is saying is whatever A is added to B, you'll get a number. And then also A times B is also a real number. So whatever A is, you multiply it by B and you get a real number. So for example, 2 plus 3 is 5. And 5 is a real number. And so 2 times 3 is 6, and 6 is a real number. The commutative property, we have a commutative property of addition and a commutative property of multiplication. And in the commutative property, it doesn't matter how you add A and B, you'll still get the same answer. So 2 plus 3 and 3 plus 2 equals 5 if I substitute A for 2 and B for 3. Same thing with A times B. So if I substitute A for 2 and B for 3, this will be 2 times 3. That also equals 3 times 2. Associative property, hopefully you can see that associative property deals with parentheses, and the parentheses are associating differently. And on the left side, the A and B are associating with each other. But on the right side of the equal sign, the B and C are associating with each other. So associative property changes the parentheses, whereas the commutative property changes the position of the numbers. So notice that in the associative property, A is still first, B is still second, and C is still third on both sides of the equal sign. Same thing in multiplication. Only the parentheses change. Also, there's an identity property where any number plus 0 is that same number. And there's a multiplication identity property. Any number times 1 is that number. There is an inverse property. There are actually 2 inverse properties. One is where the positive number plus the negative of that number will give you 0. And that's also called additive inverses, or you can call them opposites. And the second one is called the reciprocal or the multiplicative inverse, which means that if I multiply any number times its reciprocal, I'm going to get 1. So the identity property and the inverse property they're 2 properties for multiplication and addition. So you really need to be careful with what you're actually seeing so that you don't get them confused. And finally, we have distributive property where B and C are in parentheses, and A is going to be distributed to B through multiplication, and A is going to be distributed to C through multiplication. And here are some examples, and again, you can pause the video and go through the examples on your own, or you can just work straight through and see if you can figure them out. And hopefully you can see that this is the associative property of addition. And the reason why it says of addition is because they have the plus signs. Because remember, there's also an associative property of multiplication. This is the identity property of multiplication. And again, that's important because there's also an identity property of addition. See, this should be commutative.